today we're here at the Agronomy Center for Research and Education, just north of town here. And we're going to be doing a wind erosion simulation. And if you look at the table here, you can see the setup that we have. We have a wind blowing device here that has variable speeds, which is controlled by this knob here that we have, just the same way that you would do a dimmer light in your house. And then we have the soil tray, and so it doesn't have any soil in it right now, but once we begin the experiment, that is where the soil will start at. The other part of the setup that I want to point out is this device. And so that device is known as an anemometer, and it is a device that's measured used to measure wind speed. You can see that there's kind of a windmill type device in there, and the faster that spins, the quicker the wind is, obviously, and the digital readout gives us the wind speed. And so the first thing that we have to do to begin this lab is to calibrate our wind speeds that we're going to use on the different speed intervals that we have in the lab. And so we're going to do 4 different speed intervals. And so the way that we will calibrate the wind speed is we'll begin by turning on the device, and then I'll take the anemometer and I'll lay it on the top lip of the soil tray. And so what this is doing is that is giving us the wind speed at that Z0 position that we talked about Tuesday in lecture. So I'm going to go ahead and demonstrate one time how we calibrate the wind speed. So I have the device set at the first wind speed that we'll be using. And so we always want the wind to come from the back of the anemometer, and so the digital display will be facing the camera. And so while we hold the anemometer in position, I'll read the wind speed on it, and we're reading in miles per hour. And it looks like we have a wind speed of about 4 miles per hour. And so I'm going to go ahead and crank up to the second level and see what the wind speed is there. So at level number 2 on the device, the wind speed is about 7.6 miles per hour. I'm going to go to number 3. Okay, so at the third level, we're at about 9.4 miles per hour. And then we'll go ahead and do the last one real quick. Okay, so at our top wind speed, we're at about 11.4 miles per hour. And so that should give us a pretty good gradient of speeds to use throughout the experiment. Okay, so now that we've demonstrated how to calibrate the wind speeds on the instrument, the next part of the experiment is actually setting up the soil trays. And so in this experiment, we're going to use 2 different soils. And so we'll have a soil from Oklahoma as well as a soil from the Purdue Animal Science Farm. They represent 2 different soil textures. The soil from Oklahoma is a fine, sandy clay loam, and the Purdue Animal Science Farm is a silt loam. And so hopefully those 2 different textures will give us differing results between the 2 for good comparison. In order to prepare the trays, what we did was we used the same tray that we used for wind speed calibration and filled them to the top with the soils. And then in order to prevent any artificial surface roughness, what we did was we leveled the soils to the tray. And so if you can come a little bit closer and see the actual soils here, you can see that they are level with the tray. They're relatively well mixed as far as particle size distribution. We did sieve these soils using a 2mm sieve to really prevent any super large particles being in the trays. And so they're beginning on the same equivalent basis as far as particle size distribution. Okay, so to get into the soil descriptions a little bit further, so the Purdue Animal Science Farm obviously is located just north of West Lafayette here. And so it represents an area that, if you remember the map from lecture, gets a relatively high amount of rainfall, and a relatively low amount of that is transmitted as evapotranspiration. However, on the other side, we have the soil from Oklahoma. So we have a soil that receives relatively little rainfall throughout the year, and what rainfall it does receive is highly transpired, and so we see a lot of evapotranspiration in that soil. And so the soil from Oklahoma represents an aeritic soil, so low humidity, high heat. And the soil from the Purdue Animal Science Farm represents a eutectic soil. And so that's a soil that relatively high humidity, temperate heat, things of that nature. Okay, so now that we've described the soils and we have the soil trays prepared, the first thing that we're going to do is test the threshold velocity of the soils. And so if you remember from lecture, threshold velocity is the velocity needed to overcome the cohesion and actually displace soil particles. And so to do this, what we will do is we will turn the instrument on and we will slowly increase the wind speed while closely watching the soils until we see particles begin to move, at which time we will take the anemometer and we'll measure the wind speed, and that will be recorded as our threshold wind velocity. Okay, so I'll go ahead and turn the instrument on. And I'm going to slowly increase the speed as we watch for the movement of particles. There's one. There's a couple. So right now we've reached the threshold velocity. I don't know if you could see it on the video, but we do have some particles along the top edge here moving. And so what I'll do is I'll take the anemometer and I'll measure the wind velocity. Okay, and the threshold wind velocity that I found for this soil, which is the Purdue Animal Science soil, was 2.6 miles per hour. The threshold velocity for the Oklahoma soil was 6.9 miles per hour.
All right, class. In this phase of our experiment, we want to examine the objective of looking at the impact of incrementally increasing wind speed on wind erosion from the tray. And we're going to do that across soil. So one of the goals is to, as we increase wind speed, to see the impact of that on the different soil types. So one from Oklahoma and one from Indiana, from right here at this farm. All right, class, so we're going to look at the impact of increasing wind speed on wind erosion, detachment, transport, and deposition on this Oklahoma soil. All right, we're going to start with level 2 because level 1 was lower than the wind speed for level 1 was lower than the threshold velocity. Going to ease up to level 2. That's level 2 impact. We do see some detachment and we do see some transport and a little deposition on the back end, but not much. Okay. Now we're going to increase from level 2 to level 3. And we're starting to see much more detachment. And if you think about lecture today, on Tuesday, you're having creeping of particles along the surface. That's the transport. And then it's depositing on the back end. Okay, now we're going to transition from level 3 into level 4. As we're on the way to level 4, much more transition, much more detachment. That's level 4. Okay, if we can capture the deposition, so we had detachment, transport, we had deposition here from the lower level wind speeds, and then if you look here, we have deposition right from point A to point B from the higher wind speeds, namely level number 4. All right, let's look at the next soil. All right, we've just finished with the Oklahoma soil, and we looked at the impact of increasing wind speed on its wind erosion. Now let's examine the same impact of wind speed on the Mahler soil here from Indiana. So we're going to start off at level 2 and work our way up from 2, 3 to level 4 with increasing wind speeds. Here we go. So on the way to level 2 here. Starting to get already detachment, right? So this is when wind velocity overcomes the cohesion between particles. We're going to go from level 2 to level 3. Much more movement. Much more impact on the surface. That's level 3. Okay. Imagine a sustained wind like this, a gust of wind on the farm with no cover. You're losing your topsoil. Okay. Let's transition from level 3 to level 4. Wow, look at the impact. Okay. So now, if we wanted to discern differences between soils as the wind speed increased, we would then have to weigh. We had initial weight of the tray and the soil together, and then we would have to have a weight after each wind speed in order to determine the loss of sediment due to wind erosion. And then we can compare at what incremental increase in wind speed was most soil lost on average across soils, and then we can look among soils and between soils to determine differences also. And that's what you're going to be doing with the data.
Okay, so now that we've tested the effect of different wind speed on wind erosion between the two soils, we now want to look at the effect of antecedent moisture content on wind erosion across the two soils. So, antecedent moisture content, what is it? So, antecedent means prior to. So, antecedent moisture content would mean the moisture content of the soil prior to the wind event. And so, what we're going to do is we're going to use a spray bottle right here to wet the surface of the soil evenly across the surface. And so what this will do is it'll increase the moisture of the soil, and it should change the velocity at which the soil particles move. And so I'm going to go ahead and wet the soil. Okay, so we've evenly wet the surface of the soil. And so now what we're going to do is, again, we're going to start at level 2 because remember our threshold velocity for the dry soil was actually greater than level 1. And so we shouldn't expect to see anything at level 1 anyway. So we'll start at level 2 and we'll work our way up and we'll see what happens over time to the soil after we had wetted it. And so we're going to go ahead and start at level 2. And so you can see that we don't have any detachment or transport occurring. We have now increased the threshold velocity of the soil due to the increase in antecedent moisture content. So we're going to transition from level 2 to level 3 now. So we're now at level 3, and we'll let it run for a second. But again, you can see that change in antecedent moisture content really affects the cohesion of the soil, and it allows it to stick together much stronger than when it's dry. So you can see that we still have no detachment or transport occurring at the level 3 wind speed. So now we'll increase to level 4. So we're now at the level 4 wind speed. Again, we still don't see any detachment or transport occurring at this point. Okay, so you can see that we drastically increased the wind velocity needed to detach and transport soil particles just by simply changing the moisture content. Okay, so now we're going to test the effect of antecedent moisture content on the Purdue Animal Science farm soil. Again, we'll begin at level 2 and we'll work our way up from there. As you can see, again, we've drastically increased the threshold velocity. At level 2, we're seeing no transport or detachment occurring, whereas with the dry soil, we did. So we'll go ahead and increase to level 3. Okay, so we're at level 3 now. Again, no detachment or transport is occurring at level 3. So we've transitioned to level 4 now. And again, as you can see, the threshold velocity to overcome the cohesion of the soil due to the increase in the antecedent moisture content has not been reached. And so what this means is that we would need to increase the velocity of the wind even higher than what we can achieve with this instrument in order to get detachment of that soil at the moisture content that it's currently at.
All right, so a little review. We started out, we know we have 2 different soils from 2 different soil moisture regimes, one from Oklahoma, one a molly soil from Indiana. We then tested and determined the threshold wind velocity. From there, we dry. So when the antecedent moisture content was dry, we then tested the impact of increasing wind velocity on the erosion susceptibility of the soil as velocity increased. And we did that with both soils. Then we came back and we wet the soil surface to simulate antecedent moisture content where there was possibly a rain event, right? And then we then looked at the impact of wind velocity by increasing from level 2 to level 4, and we saw for both soils there was no detachment, no transport, and no deposition. And so what you're going to do is analyze the data to see if this is true. So we've demonstrated some of the principles that we discussed in lecture on Tuesday. So right now, you've already developed your hypothesis, right, on what you think would happen between these soils as we increase wind velocity. Next, you're going to analyze the data, and then you're going to write your discussion, okay? And then we're going to discuss it verbally to, again, rehash and prove to ourselves some of these principles of wind velocity in the U.S.